Okay, so can you see the screen? Yes, okay. Okay, so let's see. Let's wait a couple of seconds, see if anyone else joins. Okay, so let's start. What we ended up last time doing was to compute the, I guess one of your microphones is open. Can you maybe close the microphone if you're not talking? Mute yourself. Is it me or- I'm going to do it on your behalf. So what we have here is the maximum likelihood sort of idea. So we use the maximum likelihood estimation procedure to estimate data, and we concluded that the problem reduces to minimizing the least so the problem reduces to the least squares problem, which minimizes this let's say sum of squares of error between y and x beta, and there was a solution to this, which we got by taking the derivative, and so it led to these normal equations whose solution is this guy, and this guy is unique if x transpose x is basically invertible, and that's true if x has full column rank. So we went through this. The idea was that this estimation procedure can also be given a geometric interpretation. What we have here is minimizing least squares problem, basically, is equivalent to minimizing the distance of y and a vector mu in the image of x. And so what we get here is the problem, which is the projection of y onto the image of x. So the idea was that in order to, so our model basically, so we'll come back to this idea frequently. So our model is basically this, our model for the mean of y is this hyperplane, or this linear space. So we expect the mu to be here. So mu, remember, is the x beta, and we know that y is x beta plus epsilon. So we expect mu to be here. So y is, y is x beta plus epsilon. So this is mu. Sometimes I write star here. So this is like the true mu. The true mu vector is somewhere here. Maybe not there, but it's a mu star is the true mean vector, is in that subspace. So your best guess of mu star is to project y into that subspace, and you get the closest, basically, mu to this guy, and that would be mu hat. And then the residual, which is this vector, y minus mu hat, has to be orthogonal to the image, and we went through this idea. So expanding this led to these normal equations and also this same estimate. And also we argued that E being orthogonal to the image is equivalent to X transpose E being 0, and this is the same as kernel of E being belonging to the kernel of X transpose, so we ended up proving this identity. So this slide contains a lot of information and a lot of geometric ideas, which I hope you go through it and you understand. Okay, any questions about this? I'm gonna come back to this frequently, this picture. No questions? Okay, so we then, so there are some consequences of this, which I'm not gonna repeat. And then we went back and plugged the estimator that we got, beta hat, into the likelihood. And now we got a likelihood which is only the function of sigma squared. And then we maximized over sigma squared, which is equivalent to minimizing this other function here. So we did some sort of argument that it's equivalent to minimizing this, and then you can minimize this by taking the derivative and set it equal to 0. We ended up driving this equation, so, or this expression for sigma hat squared. So sigma hat squared is basically, this is the residual, norm of the residual squared. I wish I had written it differently. So this is saying sigma hat squared is norm of the residual squared over n. Okay, S beta hat. So that's a bad notation. Your book uses this. So S beta is this. So if I plug in S beta hat, I would get y minus x beta hat squared, which is just y minus mu squared, which is just the residual squared. Okay, so that's the little calculation here. Okay. Smaller. Okay. So that's this idea right there. Okay. So let's go back. Yeah, so what we ended up doing is that instead of actually using the MLE, which is going to be this guy, we ended up using the, or I mentioned that we use this alternative estimator, which replaces m in the denominator at n minus t plus 1. The reason is that, as we'll see, so I'm going to call this s squared, and probably most of you have seen this before. S squared is an estimate. Sorry, give me a second. Okay, so S squared is unbiased for sigma squared, and this MLE is not. So we'll see that shortly. Okay. Okay, so this was as far as we got last time. Questions? No questions. You're very quiet today. No one has any questions. Okay. Fair enough. So let's move on then. So I'm going to introduce this matrix, which you have already seen in your homework problem. So recall that beta was this, beta hat, so that's our estimate. And if I want to compute the vector of fitted values, mu hat, that would be x beta hat. So if you multiply this guy by x, you'd see that just plug this in here. So plug beta hat in here, and you end up with this matrix. Sorry, you end up with this expression. And so this matrix here is called H. or the hat matrix. So if I define H to be X transpose, X inverse, X transpose, then I can write the result as mu hat is H times Y. Okay. So nothing special. But you have encountered this matrix in your whole problems. This is an example of an orthogonal projection matrix. What this is saying is that in order to get the projection of Y onto the image of X, we can just multiply H by Y. Or pass H through Y. Pass Y, sorry, through H. I.e. form HY. Okay, so the idea is that I have this space. It's my linear space. That's the image of X. And I have my Y. And I want to find the projection onto this image. So I just multiply it by, I form HY. That would be my projection. That would be mu hat. Okay, that's how this thing works. Sounds good? Questions? So you have seen this in your homework problems. Anyone remembers properties of this matrix H?
I think it was H square equal H and H transform is equal H to property of H.
Yes, so these are the two properties. So H has these two properties. So H is symmetric, so H transpose is H is equal to H, and H is idempotent, so H squared is equal to H. So these you have shown. And the other property that I mentioned is that for any Y, HY is the orthogonal projection of Y onto the image. Okay, that's basically this fact here. Okay, so this is just this idea there. So this idempotency is what you expect from a projection matrix. So if I have a projection matrix, so what happens if I project something onto the image twice? So suppose I have, so I have this space. This is image of X. I project Y once onto this. So I project Y once, I get mu hat. So what happens if I project mu hat again onto the image of X? Anyone? No one wants to guess. Geometrically, what happens if I project mu hat onto the image of X? I'm going to wait until someone tells me something about it. No one wants to just guess. What happens if we project mu hat onto the image of X?
When we talk about the projection, we talk about the minimal distance between vector and subspace. When mu
Yeah.
hat in the subspace, that means the minimal space is 0. Exactly.
Minimal distance. So what is the projection?
Mu hat itself.
Right. So if I project mu hat, I get back this. So in order to project mu hat, I have to multiply it by h. So this geometric idea that because mu hat is in the image, its projection is itself, says that this should be equal to mu hat. Okay. Projecting mu hat onto image of x gives back mu hat. And so this is, and mu hat, we know mu hat is hy. Okay, so if you put these together, you conclude that 1 into 1 plus 2 implies, if you plug back in mu hat in that equation, you get h squared y is equal to hy. And this holds for any y. And h squared has to be equal to h. Okay, this is a geometric proof of that fact, which you can also show using the formula that you have here. Okay, so if you understand that, you would understand the geometric picture better. In any case, so h has these two properties, and any matrix that has these two properties is an orthogonal projection matrix. So we have this lemma, which I'm not going to prove. A matrix is an orthogonal projection matrix if and only if it's symmetric and idempotent. Okay, so these two properties, in a sense, characterize orthogonal projection matrices. And the space onto which such a matrix projects is the same as its image. So one of the things that you can show is that exercise. Show that image of h is the same as image of x. So I can equivalently say that h projects onto the image of itself, so onto its own image. So given any matrix h who's symmetric and idempotent, you know that it's an orthogonal projection matrix, and the subspace onto which it projects is the image of h. So you don't need to have access to this underlying x. Okay. And you can verify that I minus h is also a projection matrix because it's symmetric and idempotent. If you go through your homework problems, in one of your homework problems, you have shown this. Because it's symmetric and idempotent, it has to be an orthogonal projection matrix. And then it's not hard to verify that I minus h times y, in fact, projects onto the orthogonal complement of the image of x. So you can note that I minus hy is in fact that residual vector. So what happens is that I project onto, so this is going to be hy, and then I project, if I project onto the orthogonal complement, in this case, the orthogonal complement would be this guy. So let's do, for example, this. So that's the orthogonal complement of the image, if you recall. So it's a subspace that's orthogonal. Every vector in it is orthogonal to the image of x. So projecting onto that direction, in fact, gives you exactly this E, which is going to be I minus h y. So you can think of this as just going here. So that would be E. So we're not worried about the origin of the vector. So the vectors are, I am shifting it. So you can see that I can decompose basically y into mu hat plus E. Mu hat is in the image of x, and E is in the image per. Okay, so that's this idea. So I can write y as mu hat plus E, where mu hat is hy, E is I minus hy. You can see this identity holds because the sum of the two is y. But the key is that this piece is in the image of x. It's a projection of y into the image of x, and this piece is in the image of x curve. It's the projection of y onto the image of x curve. And this is the orthogonal decomposition of Rn that I talked about. So same as, say, V. So you can say I can write this as this plus image curve. Or in other words, so I can write it as V plus V curve, where V is image of x. So that's the same idea that we discussed before. In any case, any vector can be written as an orthogonal projection. Some of two pieces. One, a projection onto the image of x, the other projection onto the image of x. So that complements the geometric idea. Okay, any questions? Okay. If not, let's move on. So the Gram matrix is just a notation that I'm going to mention, and it's going to be useful for us. But I'm not going to spend too much time on it. So recall that we can write x as x0, x1 up to xp. These are the columns. And so we have encountered this matrix x transpose x. And if you go and verify for yourself, if I expand this, so x transpose x can be written as x0, x1 up to xp. And then transpose would be x0 transpose, x1 transpose, xp transpose. And then you expand it, you get x0, sorry, the other way around. I get x0 transpose, x1 transpose, xp transpose, then x1, so x and that xp. So we get x0 transpose x0, x0 transpose x1, dot 0 transpose xp, and xp transpose x1 transpose x0, x1 transpose x1, xp transpose x0, dot xp transpose xp. So if you multiply out these two using the vector matrix notation, so this is like 1 by n, this is n by 1, so I can multiply these coordinate wise. So you can go through and realize that this is doable. Then you just show that we have shown that, for example, the ij entry of this is just xi transpose xj, which is just the inner product of xi and xj. Okay. Then this means that in order to form this matrix, which is called the Gram matrix of these, so I just need to have pairwise inner product of these vectors. So as long as I have these pairwise inner products, I can form this matrix. Okay. For example, if all of these pairs, so xi and xj, are orthogonal for I not equal to j, or I not equal to j, then all the off-diagonal entries are 0. Okay. This is not a good notation, so this should be, if it's 0, it's fine. Let's say if it's, for example, identity, or sorry, this is good. Yeah, this is fine. So for example, if things are diagonal, so if X transpose X is diagonal, this means, i.e. X transpose X is a diagonal matrix. This means that these pairwise inner products are 0. So this matrix has interesting, useful information. And one property that you can show as an exercise using the definition, show that X transpose X is always positive semi-definite. Okay, this is useful in some applications. Okay. Questions? Sorry, something happened to this. Yes. Okay, so questions?
Professor, projection
Yes.
matrix is a kind of vector space?
Can you
Or
say that?
give a vector space?
Can you say your question again?
Projection matrix give us
What
space?
matrix?
Projection matrix.
Give you what? So the projection matrix is a matrix. So what do you mean by?
When you use it here as a orthogonal matrix,
Orthogonal projection matrix, yes.
that means this matrix makes a vector space for all projection.
I'm not sure if I understand correctly. So this is just a matrix. So
Okay.
these are classes of matrices. Do you mean, is the set of all projection matrix is a vector space? Is that your question, or?
Okay, nobody, I ask you.
Okay, no problem. So any other questions? Okay, so this is optional, but we talked about this before. The rank of the ground matrix is the same as the rank of X. And so if X is full rank, the ground matrix is full rank, and so it's invertible because it's a square matrix. We talked about this. This is optional if you want. There's a proof of it. Okay, and then there's this example which I'm going to skip in the interest of time. So you can do these things when p is equal to 1. I think your TA can go over this if you have questions. So you go through this example for yourself. This does these calculations for this simple linear regression model where you just have one covariate. And in this case, there are some simplifications or some, you can write formulas that might be familiar to you. And it will be interesting to just go over this. But I'm going to skip it. But one thing to notice is that sometimes we write beta hat like this, and it's convenient to do it. The reason why this is valid is that this y over 1 over n and 1 over n cancel out, because this 1 over n comes out as n here, and then it cancels this out. So this is an equivalent formula, which I often use, especially let's say in exams. So don't be thrown off by it. It's just the same formula. And if you go through this calculation, if you have questions, let me know. I'm going to skip this slide and move on to the idea of sampling distribution. Okay, so we have computed these estimates. These are random quantities due to the randomness in the noise, epsilon. And we would like to understand the statistical properties of these. So the distribution of these estimates is called the sampling distribution. So for example, when they say sampling distribution of beta hat, it means that they talk about the distribution of beta hat under your model. So if we can compute these things, these sampling distributions, or information about these sampling distributions, then we can quantify the uncertainty in our estimates. So the variance of that distribution, for example, gives you some idea about how variable that estimate is. So we had two sets of assumptions, E1 and E2. So E1 was assuming things about means and variances of the noise and the covariances of the noise. And under this one, we can actually compute the means and covariances of these estimates. If you want the full distribution, however, full sampling distribution, we need to assume something about the distribution of epsilon. So we're going to use E2, which assumes the Gaussian distribution for epsilon. Okay. We'll see. So some of the results, again, are generally true under E1. Some require their normality or Gaussian assumption, multivariate Gaussian assumption E2. So recall that the expectation of y is mu, which is x beta, okay? And the covariance of y is sigma squared I. Again, to remind you why this is true, we have y is equal to x beta plus epsilon, and under E1, we assume that expectation of epsilon is 0, and covariance of epsilon is sigma squared I, from which it follows that the mean of, so these two translate to these two statements. The mean of y is equal to mu. Mu is this guy. And covariance of y is also the same as the covariance of epsilon. Okay, so recall that this is covariance of epsilon, which is equal to this. Okay. Questions so far? So we just have about 1, 2, 3, 4, 5, 6, 7, 8 people in the class. So I'm gonna, from now on, take attendance. So let me just somehow, just give me a second. You can think about questions if you have, so that I will write down the names. Okay, no questions? Okay, so let's work out the properties of beta hat. So we're going to write. I'm going to use this notation. I'm going to write A, or X transpose X inverse X transpose as A. So if you go back and remember, so beta hat was X transpose X inverse X transpose Y. And so if that's the case, then I can write beta hat as A times Y. This is helpful for us, just introducing some notation. And then you can also verify that A times X is the identity matrix. Anyone wants to say why is that?
We have the same question in discussion section. Just
Okay.
write I and time X. And then because X transport X inverse and X transport X is inverse identity matrix, and the dimension is P plus 1 times P plus
1. Right. Okay. So we have, sorry, just multiply this out by this. These two matrices are the inverse of each other. So this should be identity, and the dimension is P plus 1. So we get this. Okay. So we have the first result. So under this linear regression model, beta hat is an unbiased estimator of beta. So what we have here is that the expectation of beta hat. So what does it mean for beta hat to be unbiased for beta?
When we talk about the unbiased, we just
Yes.
think about expectation. If expectation of beta hat is exactly equal beta, that means it's unbiased.
Yeah, so this is exactly unbiasedness. So expectation of beta hat is equal to beta, the parameter that you want to estimate. So an estimator is unbiased for a parameter if the expectation of that estimator is equal to the parameter for any value of that parameter. So no matter what beta is here, the expectation of beta hat is always equal to beta. So this is good. Usually you want estimators that are unbiased. The other property is that the covariance of beta hat is given by this expression. So this helps us in uncertainty quantification. Okay. So here I've written this as exercise. So you should be able to compute these. Maybe I'll do it a little bit here. So how do we prove this result? How do you show, for example, the expectation is equal to beta?
By definition of expectation, by lemma, expectation of beta, that means expectation of AY, and by lemma is A, expectation of Y, and expectation of Y, I'm
So
sorry,
expectation of Y is
X beta.
X beta. Yes. So you get A times X beta, and A times X is identity. So you get beta. Okay, so that's exactly what you should do. So lemma something, I forgot, but you use the lemma that you can pull out the matrix. This is the linearity of expectation. Okay, another way of saying it, linearity of expectation. So you can see the results that or the things that we develop are very helpful. We can use them to actually drive interesting results. So now you know that the expectation of beta hat is the same as beta, so beta hat is unbiased for beta. So how about the covariance matrix? How do you compute the covariance of beta hat?
Again, we can use lemma. The covariance of beta hat is the covariance of
A times Y, yes.
And it's A transport covariance YA. And just
yes.
plug in A.
Transpose, yes. So what is covariance of Y?
Is sigma score IN. Is the constant number. We can move it in front. And
yes, and then A times IN times A transpose. This is just A transpose A. Okay. And then just plug in and show that A transpose A is in fact, this guy is in fact X transpose X inverse. So that's the exercise that you have to do. This is just a calculation. So A is given up there, you plug it in and you get the result. Okay, so you can see thank you first for doing this. So any questions so far? So you can see that the Graham matrix, the thing that we talked about, the inverse of it appears in the covariance of beta hat. Okay, again, a statistically useful quantity. And again, because the covariances, if you remember, covariances are positive semi-definite. Okay, this is another proof that X transpose X is positive semi-definite, because the inverse of the positive semi-definite is preserved under taking inverses. So this, because the covariance is positive semi-definite, so gives another proof. So cov beta hat is PSD. To conclude, we conclude that X transpose X inverse is PSD. And from this, we conclude that X transpose X is PSD. So this is like a statistical proof of the fact that X transpose X is PSD. Okay, this you can do as an exercise for yourself. Try to argue. So this part we have shown before. This is immediate. The fact that the inverse being PSD means that the matrix itself is PSD. Try to argue that for yourself. Okay. Questions? Okay, so I'm moving a little bit fast. Just interrupt me because I want to sort of catch you up to the homework. So the basic idea is that we can repeat the process for other quantities. So another quantity of interest is mu hat is x beta hat, which also I recall is equal to hy. Okay, and I mean this is the H matrix that we defined here. Remember. So mu hat is x beta hat, which is also equal to hy. So we're going to use both. Both notations are useful, or both expressions are useful. So I would like to, for example, compute. So this is the vector of fitted values. I'm going to show that mu hat is unbiased for estimating mu, the mean vector. So mu hat you can think of as an estimator, which is unbiased for mu. So if I plug this in here, the expectation. So this is equal to the expectation of x beta hat. I can pull out x. I get this next expression by that lemma. And then beta hat is, expectation of beta hat is just beta. That's what we just showed. And x beta is just mu. Okay, this proves that the expectation of mu hat is mu. The second approach is we can prove the same thing using the other notation. So mu is x beta. So mu should be in the image of x because it's written like x beta. So if I multiply h by mu, I would get mu itself. Okay, this can be verified using the formulas, using this and the formula for h, but also has a geometric interpretation. Anyone knows the geometric interpretation of this? Why h mu is equal to mu?
It's because h mu is equal to mu because we're projecting mu onto the image of x.
Great, yes. And
basically, so, and mu is equal to hy, so we have that the h is both symmetric and idempotent.
Right, but that part is okay. So why? So h mu is the projection of y onto the image of x. Okay, so we're claiming that projection is equal to mu. Why is that? So like geometrically, why is that? It was close. Your explanation was close. So what vectors get the same projection as themselves? What should the vector be for it to get the same projection as itself?
It's orthogonal. Orthogonal?
No. So if it's orthogonal, the projection would be 0. So if I have an orthogonal vector, so if the vector is orthogonal to the image, then when I project it, I get 0. It should be in the image. So if mu is in the image, then the projection would be itself. Okay, so it should be the opposite of orthogonal to the image. So because so that's the idea. So mu is in the image of x, because mu can be written as x beta, and anything in the image of x, when you project it, you get back itself. So this is saying projection of mu onto image of x is itself. because mu belongs to the image of X. Okay, and you can also verify it directly. Just try to verify it directly, okay? So if that's the case, then what I would get is that I plug in mu hat here, so I get hy, and then I pull out h, I get this. I know the expectation of y is mu. This is again from these properties. The expectation of y is mu. So what I would get here is h mu, and then h mu is equal to mu. So that's what I just mentioned. So that's another way of doing it. Okay. Okay. So so the covariance matrix is, how do we do the covariance matrix? Anyone? Okay, I'm gonna do it myself. So covariance, I mean, we're basically doing it here. So covariance of mu hat is covariance of hy. That's the formula. And then I get, this is equal to covariance of y h transpose. Okay, and the covariance of y is sigma squared in. So I get this expression. I can pull out sigma squared out, and I can replace h transpose with h. Why can I do that?
Because H is
Idempotent, yes. Not idempotent, because h is symmetric. Right? Because h is symmetric is that this is h squared, and h squared is equal to h. This is because h is idempotent. So h is symmetric. H is idempotent. Okay, and so you get sigma squared h. So that's the covariance of mu hat. Okay. Questions, comments? So these are not difficult. So once you understand how to compute expectations and covariances, then you use some of the properties of these objects to simplify the expression. Okay. Questions? So let's move on. So we're going to go to residuals. We can do the same for residuals. So residuals are, again, can be written in multiple ways. Either you can write it as E equal Y minus X beta hat, or I can replace X beta hat with mu hat, or I can, again, recall that I can write this as, so I can write this as E is equal to Y minus mu hat, which is equal to Y minus HY, which is equal to I minus HY. So these are all valid formulas. Okay. So if you go through the calculation, you plug this expression here. So expectation of E is expectation of Y mu hat. I can write this as expectation of Y minus expectation of mu hat. Okay, that's equality. So why is that equality correct?
Because expectation is linear.
Yes, using the linearity of expectation. And then we just showed that the expectation of mu hat is mu. Okay, that's what we showed here, right? So I plug it in and I get that mu's cancel, so the expectation of the residual is 0, which is good, which is what we hope for. So the residual vector has 0 mean. And then we can compute the covariance. So covariance of E is equal to the covariance. I'm going to use the other expression. So this times Y. This is going to be I minus H times covariance of Y times I minus H transpose. This is sigma squared IN. So what is I minus H transpose?
Again, symmetric.
Symmetric, yes, because I minus H is another projection matrix. So this is going to be sigma squared I minus H squared. And then this is going to be equal to sigma squared I minus h because what?
Again, item.
Yes, I minus h is idempotent. Okay. Because it's a projection matrix. So you can see these properties simplify the calculation. Otherwise, you can expand it and try to do this, but that's what it is. Okay. Okay. Sounds good? Questions? Okay, so we have calculated properties for like beta hat, mu hat, statistical sort of quantities. What is interesting here, which I'm going to spend some time on, is we can do more. Okay, what else we can do? We can actually like provide something about the joint distribution of beta hat and E. Okay. So let me just ask here. So suppose I have this, I've shown this. Maybe, yeah, so this part. What happens if I assume E2? What happens if I assume that Y is actually, so if we further assume E2, which means that epsilon is normal, which means you're on covariance sigma squared IN, then Y is multivariate normal would mean mu and covariance sigma squared IN. What can I conclude about beta hat? Can I conclude that it has a certain distribution? So this was under assumption E1. So we didn't use normality here. But let's say if I add the normality assumption, what can I say about beta? Can I determine the full distribution of beta hat? Anyone? So here, Y has multivariate normal distribution, and I'm multiplying it by a matrix. What can I say about the resulting vector? What is the distribution of beta hat? Doesn't ring a bell? No one wants to comment on this? So what was the first property of multivariate normal distribution that we discussed? Anyone remember? No one remembers the properties? What happens if I multiply a vector, multivariate normal vector by a matrix? Is the result a multivariate normal random vector?
Yeah, I put that.
Go ahead. What was that?
Oh, I put that it was also MVN just because like you're multiplying a vector by something multivariate, so you're
Yes,
so yeah, it would also.
Yes. So this is an example of affine transformation. So this is like a times y plus 0. So an affine transformation of y, right? And affine transformation of y. So hence, this is going to be multivariate normal. And then we calculated the mean. The mean is beta, and then the covariance is sigma squared x transpose x inverse. So these are not going to change. So these come from these calculations. Okay, thank you. So that's what you have to recall. So okay, so if you add the E2, you get the extra information that beta hat is also multivariate normal, but then the mean and the covariance are going to be the same as what you have calculated before. These can't be different. Okay, so this is a good thing to remember. Under E2, we have this result. So now, what should we do? Or we can do the same here. So again, mu hat here is an affine transformation of beta hat, which is going to be multivariate normal. Or you can say it's an affine transformation of y, again, a matrix times y, which is multivariate normal. So we conclude that mu hat is also going to have multivariate normal distribution. Same goes for E. So E can be written as a matrix. You can see I minus h times y. And if y has a multivariate normal distribution, E is going to have a multivariate normal distribution. So all of these guys that we calculated, the mean and the covariance matrix for, are going to have also a multivariate normal distribution under the assumption E2. Okay, that's just follows from the first property, affine transformation property of multivariate normal distribution. Okay, so now I want to do something more interesting. I want to compute, determine the joint behavior of beta hat and E. And you'll see what I mean by this. This gives us more information that what we just calculated. So again, recall that A is, I just defined A to be this, and then beta hat is AY, and we also have E as I minus H times Y. The next step is interesting, which is I can write this vector as a matrix times Y, and that matrix is going to be this guy. Okay, why can I do this? This is basically the block sort of multiplication idea, if you have seen it before. So A, what are the dimensions of A? Anyone tell me what the dimensions of A are? So let's maybe do this. So this is P plus 1 by 1. Y is N by 1. So what will be the dimensions of A if this product is going to work out? This is a P plus 1 by 1 vector. This is an N by 1. So what should be the dimensions of A be?
P plus 1 times n.
Yes, P plus 1 times N. So how about the dimensions of I minus H? So this is N by 1. This is also N by 1. I assume that you said N by N. Okay, good. So now I'm going to do this. So I'm going to put A here. So let's say we know that P plus 1 is less than N. So I'm going to, if I put A here, A would be something like this. So that's P plus 1. This is N. So that would be A. And then I can put I minus H below it. So this would be I minus H. It should be a square, more or less. Should be roughly a square. Unfortunately, it's not, but assume that it's square. So that's I minus H. And then I'm multiplying it by Y. Okay, this is Y. And Y is, let me do a different color. Sorry, let's try different color. Let's do it this way. Okay. So this is n n by 1, okay? And so you can see the dimensions, the inner dimension of this and this match. The inner dimensions are n, okay? And the same goes for this. The inner dimension of this and this matches. So when you go try to multiply, you multiply each row of this by y to get the entries of the resulting product. You can verify for yourself that this is equivalent to just writing this as, so the first half would be a times y. That would be p by, let's do this. It's just going to be like this. This is going to be, more space here. This is going to be a times y, and this is going to be I minus h times y. Okay, this is going to be n. It's going to be p plus 1. This is going to be 1. So what you end up doing is that basically what I'm saying is this is going to be equal to a times y, I minus h times y, which is what it should be. So beta hat is this, E is this. What I'm doing is that I'm pulling these two matrices out and putting them here, and then do this as this whole matrix times y. And this is valid if you think of this in terms of these blocks. So this block gets multiplied by this, gives me that. And this block gets multiplied by this, gives me that. So just go and verify that this is actually a valid identity. So what I'm saying here is this identity. So it's valid. Verify for yourself. So picture. That's the picture. Okay. Questions about this? Yeah, I've done similar things in your work problem. So, and it's also going to probably show up in exams. So when I say, for example, find out the joint distribution of beta hat in E, the most useful thing is to write them as a matrix times some other vector that you know the distribution. In this case, we know the distribution of y, and we've managed to write this as a matrix P. I'm calling this P. So we have written this as beta hat E is a matrix P times y, and this matrix P is P plus 1 plus n times n. This is n by 1, and this is P plus 1 plus n by 1. Okay. Does that make sense to people? So if this is the case, then you can write down the expectation. For the expectation, we don't need this sort of machinery. You can use this machinery, but you can also just directly say that the expectation of this vector, I can move the expectation inside, and I get beta and 0, which we computed before. This doesn't give us extra information to just verify that this is the case. So the expectation of this vector is beta and 0, because the expectation is coordinate-wise, basically. You can just move it inside. X works in blocks as well. What I'm going to do, I'm going to compute the covariance matrix of this, which is much more interesting. And for the covariance matrix, I'm going to use this identity. So H can be written as this the definition. And if you recall what A is, you can see that X times A is also another way of writing H. Okay. Right, so this is A. If I plug A here. So A here, right? Plug it in here, and then you see that X can be written as, H can be written as X times A. So let's now do the covariance. How do we compute the covariance matrix of beta hat E? How should we compute this? I'm going to use that representation that I have P times Y. Okay. What is the next step?
You would take out the P and write P times covariance Y times P transpose.
Great. Okay, so now what is covariance of Y?
Covariance of Y is
You have it here.
oh, okay. Covariance of Y would just be sigma squared I.
Yes, okay. So this is going to be sigma squared I. So what would be the next step here?
Then you would so you have P times sigma squared I. Basically you could put the sigma squared in the front,
Yes.
and then the P transpose just becomes P because P is symmetric. Or if
No, let's say you just
it's
move
symmetric.
like one step ahead. So what is the thing? What should I do with I?
I is just in the middle.
Right.
Yeah.
So what is the next simplification that we usually do here? So it's going to be a sigma squared P times P transpose. Right. I can just ignore the I didn't.
Okay.
Right. But P is not symmetric. Right? You have to be careful. So let's see why it's not. So what is P transpose? If it's symmetric, then P transpose has to be equal to P. So P, we can write it as this, transpose. And this is a block matrix. So anyone knows how to transpose a block matrix?
Is it to treat the two blocks as like as the numbers, like so it's
Yes.
A transpose and in the same row the second column is I minus H transpose.
Great. Yes. You treat them as numbers, as if these are two numbers. So you transpose the column vector becomes a row vector. So you get this, but then you also have to transpose on the entries because the entries are actually not the scalars, they're matrices. So you get this. Okay. In general, if I have A, B transpose, this would be A transpose, B transpose. Okay. General rule, do this. Okay, so now what is I minus H transpose? Let me do it a little bit better here. Sorry. Wait. So what we have here is P is equal to A I minus H, so P transpose, and then this is going to be A transpose I minus H transpose. So what is I minus H transpose?
And it's still I minus H.
Why?
Because it's a projection matrix.
Yes, so exactly. So this is a projection matrix, it's idempotent, so you get this, but A transpose is not equal to A. So what is A transpose? Anyone?
It's X and it's still the inverse of X transpose X.
Yes, so you get the transpose of this times the transpose of this. Transpose of X transpose is that. And transpose of X transpose X inverse is symmetric. So the transpose of this part is the same. Okay, again, remember that these should become second nature by the end of this course. AB transpose is B transpose A transpose. Okay, so this is going to be that. So you can see this is not necessarily symmetric. So A transpose is not equal to A. In any case, I have that, and I'm going to just use this. So this is done. So now I'm gonna continue with this calculation. So I have sigma squared. I'm going to replace this with P, which is A I minus H, and then P transpose, which is A transpose I minus H. Just bear with me for a second or one more minute and we're done. So what is the next step? Anyone? So this is a tricky part. So the dimensions match. And so what I can do is I can treat this as if the entries are just numbers. Okay, so I can multiply out as if I'm multiplying two vectors. So sorry, one column vector times a row vector. So I get this. This is block matrix multiplication because the dimensions sort of conform. I get this. Okay, this you have to verify for yourself. It's like tricky, but that's what you get. So you get a block matrix like that. So this we have seen is equal to what? It's equal to I minus H because I minus H is idempotent. A transpose A is equal to, you can verify that this is X transpose X inverse. We did this in the calculation of the beta. And this one, you're going to show for yourself that this is actually 0. This is the transpose of it. This is going to be also 0. So what do you end up showing it? That sigma squared X transpose X inverse 0, 0, and I minus H. Okay? Or if you want, you could write it like this. Sigma squared here, and then sigma squared here. Okay, so these two parts we have already shown. So this is going to be the covariance matrix of beta hat. This is going to be the covariance matrix of E. But what we have shown is that the cross covariance is 0. And because we're out of time, I'm going to come back to this and follow through the consequences. Any questions? So this is the calculation here. And then you can read the important consequences. Unfortunately, we don't have time to go through this, but for the next time, we're going to come back and go through that. Okay, any questions? Okay, no questions then. Thank you. Don't forget to check CampusWire, and I'll have office hours tomorrow, hopefully at 5, and see you. Okay, goodbye.